Energy and power of continuous time signals. The energy of x of t is defined to be the area of its magnitude squared waveform. Using the property that magnitude squared of x of t is a product of x of t and its complex conjugate, we obtain the second equivalent expression. That was a definition that holds for both real or complex valued x of t. If we know that x of t is real, then its energy is simply the area of x squared of t. In these calculations, units of energy are usually not specified. This is because we use energy to compare one signal with another as far as their relative capability to do work, and are not so much concerned with the exact amount of work that is done. For example, if x of t and y of t are voltages versus time, and we calculate y to have twice the energy of x, then we can predict y will heat up a resistor twice as much as will x when applied across it. But as for exactly how much heat is dissipated in the two cases, we don't care. Let's calculate the energy of e to the j omega t multiplied by rect of t. Since the magnitude squared value of a product is a product of magnitude squared values, we obtain the simplification shown here. Noting e to the j omega t has magnitude 1 for all time, all that remains is to integrate the magnitude squared of rect of t. But rect of t magnitude squared is equal to rect of t, giving the result energy of this signal is equal to 1. Or we could have calculated energy using the method of area under x of t times x conjugate of t. The conjugate distributes over a product, which gives this integral, where the powers of e add to 0 and rect squared simplifies to rect, resulting again in energy value equal to 1. Here's an example that demonstrates why energy is not a suitable measure for all types of signals. When calculating the energy of complex exponential e to the j omega t, we obtain the result infinity. That's because e to the j omega t has magnitude 1 and goes on forever. It's just like saying that a voltage source connected to a light bulb will deliver an infinite amount of energy to the light bulb when measured over all time. The energy delivered per unit time, however, is finite. This consideration leads to the definition of signal power, shown here. It is measured as the energy that x of t has in a time interval of width capital T, divided by capital T, in the limit as capital T goes to infinity. Thus, power of x of t is essentially a measure of its energy per unit time. Calculating power of e to the j omega t now proceeds as follows. The magnitude of this signal is 1, and the area of its magnitude squared value within the interval minus capital T over 2 to plus capital T over 2 is capital T. This gives the result that power of e to the j omega t is equal to 1. The power measure is useful in cases when the signal energy is infinite, such as for e to the j omega t and other periodic signals. Here are some useful properties to remember. When x of t is multiplied by a constant, both its energy and its power are scaled by the magnitude squared value of that constant. Also, in general, the energy of a sum does not equal the sum of the energies, and the power of a sum does not equal the sum of the powers.